So we're ready to start the modeling process. We're going to create a couple of models to illustrate how we would do an exercise in real life. Um, let's start with model 1, and that would be a model containing every single predictor with no feature selection, that is, no variable selection in it. We're going to call this the full model, and like I said, it's just gonna be um, the model containing every single predictor with no variable selection. So let's call it full using the GLN function on the target B variable. To select all the variables, we're just gonna put a dot um, in the predictors, and that should select every variable in the dataset except um, the response. We're going to select the data to be the training data set, and we're going to set the family of the model to be a binomial so that we can do a logistic regression. Right? We want to do in the options, let's put the scientific penalty to be 999 so that we can show all the decimal points in it. And let's get the summary of the model. Now you can see why this model might not be good in practice, at least with the number of degrees of freedom for some of the variables. Um, Specifically, the demographic cluster with 53 clusters comparing against the um, the reference class, that is a variable that might need some modification before we impute it in the model, or before we use it in the model. But for now, let's just assume that we want to use it as it is and leave it in the model just as it is. At least one of the classes is significant, so that means that the variable demographic cluster gives some information on the probability or the odds of the donors donating. Um, so let's do quickly a check of adequacy in the model. We can see that the null deviance went from 6,713 to 6,420. And if we want to check a p-value for that, we want to do 1 minus um, the chi-square probability distribution function, and we want to put the null deviance minus the residual deviance, and then subtract the degrees of freedom as well, so that we can have um, the p-value. And essentially this is going to be 0 because at least one of the variables is important in predicting the response, which is the probability that that the donors donates. Um, One thing we want to check sometimes is if the variable is specified correctly, and because this is the full model, we're not going to do feature selection. But ideally, you would want to reduce the degrees of freedom of the model by dropping the variables that don't appear to have any significance. Um, Interpretations in this case of the parameter estimates, you would just do, let's take for instance the gift time last, which means the how much the person gifted, or the donor gifted the last time. And we can say, well, as the amount of the gift increases by $1, then on average the log odds of that person donating again decrease by 0.04. And again, this interpretation is probably not as easily understood, so we might have to change that into in an interpretation relating to the odds of donating. So we want to have that exponentiated, and we get these is the factor by which we would multiply the odds. So the interpretation in this case is as these uh, the amount of the gift the last time increases by $1, then the odds of donating again will change by a factor of 0.96. So that means they decrease by about 4%. So if we want to see um, the exact number, that would be in terms of percentages, that would be about 3.6%. So the odds of donating again decrease by about 4% for every dollar donated the last time. And we again can check the other variables. Again, this model seems a little bit um, too large to be useful. That doesn't mean that could not translate into a good predictive model. I mean, but it seems that there are many variables that don't appear to have any significance, so we might be better off by dropping those to have a model that is more streamlined. So that is our model number one. And one thing we want to do with it uh, right away is to get the predicted values, predictions for the validation data set. So we will do that right there. So we'll call it P4. And that is, we can do the predict function using our model. And we called it full. And our new data is the valid data set. And we want to do the type is equal to response. Okay. So those are the predictions for the validation data set. So you can see that it should have the same amount of observations. Okay, so P4 should be 4,843, which is the same amount of observations on the validation data set. A couple of things that we can check for this is, first of all, how good the model is right now. I mean, how good is the model differentiating or separating the donors versus the non-donors? And we can do this by taking a look at the ROC, or the area under the curve. So just before that, let's do, if you want to get the predictions of this model under the training data set, then you can do, so let's do this here. Let's say p4 dot train, and this would be the predictions on the training data set. We can do the same thing, predict full. We don't have to do new data anymore, because this data is already where we predicted, where we made or built our model. And we can do the same thing here, type is equal to response. And now we have the predictions for the training data set and the predictions for the validation data set. Let's create the ROC for the training data set. So let's check how much area under the curve we have for the training data set. So let's put it here, AUC for the training data, and we can do that using the PROC function, and again, I haven't installed it here in this computer, so let me just go ahead and do that. Alright, so having done that, let me call the function, the package one more time. So we want to do, let's save these AUC, these ROC numbers. Let's save it into an object named R1 dot train. So we want to use the ROC function, and we want to use the training actual value, and we want to have the p4 dot train, and that would be the values for the AUC on the training data set. So let's take a look at the AUC value, and we can find that the area under the curve is 63%, 63.8% under the training data set. So we can plot it also. We named it R1.train, and let's see, let's do it one more time. So we can see the area under the curve for this model here, which is of course larger than the baseline model, or a random assignment of donors and non-donors. So we can see that the model does better than random, but it doesn't appear to be like a very good model. And again, good depends on the data set. So this is at least we know that it's doing better than random. Let's do the area under the curve for the validation. And again, this is where you would find where you would want to base your conclusions on the validation data set. So we will change this to valid, and then change this, we named it P4. So this is here, and then let's take a look at the area under the curve for the validation. So we have here 59.4, which is lower than the training area under the curve, and that's expected. Most of the times, the performance on the validation is actually worse than the training, and this is the reason for that is that the model is actually trying to feed more closely to the training data set where it was trained. These numbers being, if these numbers are too different, that's an indication that the model is probably overfitting. In this case, we can see the area under curve under for the training to be 64% compared to 59. So there's at least some amount of overfitting in there. It's probably not too bad, but you can see the results of having all of these variables in there, especially those variables that are not significant statistically.